Good afternoon, everyone. Welcome to our first webinar. I hope you are able to hear me, and hope everybody is safe and doing well. So, because of the present circumstances, we are starting now. We are having our seminars online, and it's very pleasant to see that we're able to reach out to people whom we couldn't have reached in the normal circumstances for our seminars. So welcome you all from various parts. I can see there I can see people from outside Delhi, and it's very nice to see them. And today's speaker is Hemant Mishra. Before starting with the seminar, I will just for the smooth running, I request you all to keep your audio on mute, and there will be a question answer session at the end of the talk. But nevertheless, if you want to ask some question in between the talk, you should use the raise hand feature. In fact, at the end also for coordination, it's better to use raise hand feature, and then only unmute your audio when a signal is given from the coordinator. The coordinator is Professor Arup Pal. You could see him as the host. And if you want, in fact, you can post your question on chat to everyone or to the coordinator. So he can put up your question at an appropriate time. So it's your choice. So, and welcome all. And let's start with the talk. So Hemant would be talking on subdifferentials and directional derivatives of symplectic eigenvalues. Yes, Hemant.
Thank you, ma'am. I'll begin by sharing my screen. Yeah, I hope everyone can hear me and see my screen. Hello, everyone. My name is Hemant Kumar Mishra. I'm a PhD student at ISI Delhi. I'm doing my research under the supervision of Professor Tanvi Jain. Today, I'll be talking on Fenchel subdifferentials and first order directional derivatives of symplectic eigenvalues. So last year, I presented our work on the differentiability and other properties of symplectic eigenvalues. And today's talk is based on a continuation of that work on symplectic eigenvalues. So I'll begin with recalling some notations and terminologies. Yeah, by J, I'll denote the 2n cross 2n real matrix in block form 0, in minus in 0. Here in is the n cross n identity matrix. And by SP2n, we denote the set of 2n cross 2n real matrices M that satisfy this condition M transpose Jm equal to J. And we call this set the set of 2n cross 2n symplectic matrices. With this condition, we can see that this matrix J itself is a symplectic matrix. It satisfies this condition M transpose Jm equal to J if you replace M with J. This set SP2n is a group under multiplication, and it is also closed under transpose, meaning if M is a symplectic matrix, then its transpose is also a symplectic matrix. We will denote by P2n the set of 2n cross 2n real positive definite matrices. There's a well-known theorem called Williamson's theorem, which says that for all positive definite 2n cross 2n matrices A, there exists a symplectic matrix M such that M transpose AM is equal to the diagonal matrix in the form D00D. Here D is an n cross n diagonal matrix with positive diagonal entries D1, D2 up to Dn arranged in ascending order. We call these numbers the symplectic eigenvalues of A. When you arrange these numbers in ascending order, these numbers are unique, meaning for every positive definite matrix A, there is this number dja is unique. we're going to call it the jth symplectic eigenvalue of A for simplicity. So we get a map from P to N to the positive set of positive real numbers, A going to J of A. So we have essentially been studying the properties of these symplectic eigenvalue maps. We call these maps symplectic eigenvalue maps. Let us begin with the most obvious one, the continuity of these maps. The matrix iota A power half J power half is a Hermitian matrix. Here iota is the imaginary number and A power half is the positive square root of this matrix. A is the 2n cross 2n positive definite matrix and A power half is the matrix square root of this matrix. This matrix is Hermitian matrix and it's a 2n cross 2n matrix. Its eigenvalues are plus minus the symplectic eigenvalues of A. This is a connection between the symplectic eigenvalues of A and the eigenvalues of this Hermitian matrix. So there are n negative eigenvalues of this Hermitian matrix and n positive eigenvalues, and these positive eigenvalues are nothing but the symplectic eigenvalues of A. Now, if H is any m cross m Hermitian matrix, denote by lambda 1, lambda 2 up to lambda m, the eigenvalues of this Hermitian matrix in ascending order. Hermitian matrices are known to have only real eigenvalues, so this arrangement is possible. So for Hermitian matrices also, we get maps H going to the jth eigenvalue. So from here, for this Hermitian matrix, we see that the jth symplectic eigenvalue of A is nothing but n plus, the jth symplectic eigenvalue of A is the n plus jth eigenvalue of this Hermitian matrix. So dj of A is equal to lambda n plus j of this Hermitian matrix. So we can see that this symplectic eigenvalue map is a composition of two maps. To see this composition, suppose this is the symplectic eigenvalue map. Consider this map A going to this Hermitian matrix iota A power half J power half, and this Hermitian matrix going to the n plus jth smallest eigenvalue of it. And we know that these two quantities are equal. So in other words, the symplectic eigenvalue map dj is a composition of these two maps. Now it is known that the map A going to the square root of A is a continuous function. In fact, it's a smooth function. And it is also well known that the jth smallest eigenvalue map is a continuous function of Hermitian matrices. So our function dj is a composition of two continuous maps. So it is also a continuous map. So what we got is the continuity of symplectic eigenvalues directly through the continuity of Hermitian matrices. The literature of Hermitian matrices is very rich. In particular, differential and subdifferential properties are studied in much detail for Hermitian for eigenvalues of Hermitian matrices. So one can try studying the similar properties of these symplectic eigenvalue maps through this composition that we saw. But this direct approach represents some difficulties, especially when working with differential and subdifferential properties. This square root map makes things difficult. So from the beginning itself, we endeavor to develop an independent theory for symplectic eigenvalues in order to study the properties of symplectic eigenvalues much deeper. Now let's talk about the differentiability briefly. It turns out that these DJ maps are not differentiable in general. Let me explain that with the help of an example. Consider this example. Phi is a map from open interval -1 to 1 to the set of 4 by 4 positive definite matrices. Phi of t is this diagonal matrix. Phi of t can be seen to be a very simple map. It's a very simple matrix. It's a diagonal matrix. If you so this is of the form D00D from the beginning. So it's in the simplest form, and its symplectic eigenvalues are nothing but 1 and 1 plus t. So if we consider the first symplectic eigenvalue of this matrix phi of t, it is given as a function of t, which is defined as a piecewise function. So this represents d1 of phi t is the first symplectic eigenvalue of phi t. If you draw the graph of this function, we get this graph. And from the graph, we can see directly that this map is not differentiable at t equal to 0. So what we have this phi t, which is a differentiable map, but this composition d1 with phi as a function of t is not differentiable at t equal to 0. So that means this map d1 is not differentiable at phi equal to phi 0, because if d1 was differentiable at phi 0, then its composition with phi would also have been differentiable at equal to 0, which is not the case. A similar argument also shows that d2 is not differentiable at phi 0 as well. So this is an example in the space of 4 by 4 positive definite matrices. One can extend this example for higher order spaces also and get the same conclusion. So from here, we see that DJs are not necessarily differentiable in general. Let me quickly define the multiplicity of a symplectic eigenvalue. A symplectic eigenvalue D of a positive definite matrix A is said, its multiplicity is defined as the number of symplectic eigenvalues of A that are equal to this symplectic eigenvalue. Here in definition, this is the indices for which the symplectic eigenvalues of A are equal to D, and its cardinality is precisely the number of symplectic eigenvalues of A that are equal to D, and this is called the multiplicity of the symplectic eigenvalue. We call a symplectic eigenvalue simple if its multiplicity is 1. In other words, a symplectic eigenvalue is simple if none of the other symplectic eigenvalues of A are equal to that symplectic eigenvalue. So in our earlier work, we proved that these DJs are differentiable under a special condition. If DJ of A is a simple symplectic eigenvalue of A, then the map DJ is differentiable at A. In fact, it turns out to be smooth at A. In the above example that we saw, observe that phi of 0, if you substitute t equal to 0, it is nothing but the 4 by 4 identity matrix. And for the 4 by 4 identity matrix, it has two symplectic eigenvalues, both equal to 1. So in this case, we can see that D1 of phi 0 and D2 of phi 0 are equal, meaning both of them are not simple. And this is the reason why D1 and D2 in our example was not differentiable, because of this higher multiplicity. So DJ are not differentiable that we saw. And what about the weaker properties for these maps? So there are actually some weaker notions of differentials called subdifferentials. And we became interested in studying the subdifferential properties of these maps. And subdifferentials are useful in non-smooth optimization. Several optimization conditions can be given in terms of subdifferentials of maps. One can find more about subdifferentials and its applications in optimization in this textbook by Convex Analysis and Nonlinear Optimization by Bodwin and Lewis. The one we are going to discuss about is known as the Fenchel subdifferential. And there is a reason why we became interested in this particular subdifferential that will be revealed in a moment. Let us set up some notations. By Sn, I'll denote Sn as the n cross n real symmetric matrices with inner product of AB defined as the trace of AB for all symmetric matrices A and B. By script O will denote an open subset of Sn, and F will be a real valued map on this open set. And now I'll give the definition for Fenchel subdifferential. Actually, the notion of Fenchel subdifferentials exists for more general spaces, like non-linear spaces. But for our talk, we are only going to talk about functions on the set of n cross n real symmetric matrices. So, the Fenchel subdifferential of a function f at point A is defined as the set of matrices psi satisfying this condition, this inequality. Inner product of psi with h minus a less than or equal to f of h minus f of a for all h. So this set is said to be the set of Fenchel subdifferentials. Let us try to calculate the Fenchel subdifferential of a function. Consider this modulus map, the modulus map on the set of real numbers. Now we can view the set of real numbers as the set of 1 cross 1 symmetric matrices, where the inner product is given by the usual product that we are familiar with. So the subdifferential of this modulus map at 0 is the set of all real numbers alpha satisfying that condition. Alpha inner product with beta minus 0 is less than or equal to f of beta minus f of 0. Now this condition is same as alpha beta less than or equal to modulus of beta for all real betas. And this condition is satisfied precisely by the numbers in the closed interval -1 to 1. So the Fenchel subdifferential of this map at 0 turns out to be the closed interval -1, 1. We can also talk about the subdifferential of this function at other points. By a similar calculation, one can calculate the Fenchel subdifferential of this modulus function at other points, which turns out to be singleton 1 if you are considering the point positive, and it is -1 if you are considering the point negative. Now, in the above example, you see this modulus map is not differentiable at the point 0, but it is differentiable at every other point. In fact, its derivative at positive numbers is 1, and its derivative at negative numbers is -1. So here we can, from this expression, we can see that the Fenchel subdifferential of this modulus map at all points not equal to 0 is the singleton containing the derivative of that function. In fact, it is one of the properties of convex functions that are differentiable. So so this is one of the properties which says that the Fenchel subdifferential of a convex function, which is already differentiable, turns out to be the singleton containing the derivative of that map. We will see some more interesting properties of convex functions with respect to directional differentiability and Fenchel subdifferentiability. And these properties are going to lead to interesting results in our case. We recall the definition of directionally differentiable. What is the meaning of directionally? What is the meaning of a function to be directionally differentiable? A function f is said to be directionally differentiable at a. So this function f and a are all that we defined earlier. So if this limit exists for all h, this limit f of a plus th minus f of a divided by t, where t is going to 0 from positive side. If this limit exists in R, that is a set of real numbers, for all h, then we say that the function is directionally differentiable at A. And we denote these limits by f prime AH. And we call this map which is a map of h, the directional derivative of this function at A. Also recall the definition of convex functions. For that, let O be an open as well as convex subset of Sn. Here, then a function f, a real valued function f on this convex set is said to be convex if this inequality is satisfied for all alpha between 0 and 1 and all A and B. Now, if O is again an open and convex subset of the symmetric Sn and A is an element of O, suppose F is convex set, then the following properties are satisfied by F. Its subdifferential, its Fenchel subdifferential turns out to be a non-empty set. It's convex as well as a compact set. The convex function F turns out to be directionally differentiable at A. And the third, and perhaps the most interesting property is that you can find its directional derivative using this formula called Max formula, which uses the Fenchel subdifferential of this function at A to calculate its directional derivative at A. These properties are going to be very useful in our work later. So Fenchel subdifferentials can be used for convex functions to find their directional derivatives. In 2015, Professor Rajendra Bhatia and Professor Tanvi Jain gave an extremal characterization of the sum of first m symplectic eigenvalues. It says that twice the sum of first m symplectic eigenvalues of A can be written as a minimum of these linear maps over matrices M, where this minimum is taken over a real 2n cross 2m matrices M that satisfy this condition, M transpose Jm equal M transpose J2M, M transpose Jm equal to J, where these J are of specific sizes. For example, J2M is the symplectic matrix that we defined in the beginning, 0, Im minus Im 0. And these N and M represent the different sizes of this matrix J2M. So with this extremal characterization, one can directly verify that the map A going to the sum of twice the sum of first m symplectic eigenvalues is a concave function. So with this characterization in mind, we define this map sigma m from P to N to R given by the negative of the previously defined concave function. Therefore, this sigma m is a convex function. Now, this is a key idea in the study of subdifferential properties and directional derivatives of symplectic eigenvalues, because now sigma m is convex function. One can talk about its Fenchel subdifferentiability as well as try to calculate its directional derivative using the Max formula. Remember that Max formula gives you the directional derivative of convex function using its Fenchel subdifferential. So what we are going to do is we will find the Fenchel subdifferentials of these maps sigma m. After that, we calculate the first order directional derivatives of sigma m using the Max formula. And after that, we find the first order directional derivatives of dm using the first order directional derivatives of sigma m functions. And how do we do that? That we will see later on. Before moving further, let me introduce some numbers. Non-negative integers im, jm, and rm. So A will be fixed. A is a 2n cross 2n positive definite matrix fixed, and m is a positive integer less than or equal to n fixed. For these two fixed quantities, we define three non-negative integers satisfying the following conditions. Rm is equal to im plus jm, which is the multiplicity of this symplectic eigenvalue dm. Recall the multiplicity of a symplectic eigenvalue is the number of symplectic eigenvalues of A that are equal to that symplectic eigenvalue. The integer im has to be greater than or equal to 1. And these indices and these numbers have to satisfy this particular condition as well. Now, these terms in the equality represent the Rm symplectic eigenvalues of A that are equal to the symplectic eigenvalue Dm of A. To understand the nature of these numbers more clearly, let me explain this through diagrams. Suppose that these blue dots represent the indices from 1 to n, and m is somewhere in between 1 and n. Suppose these vertical lines represent the values of symplectic eigenvalues corresponding to these indices. Note that from the beginning itself, we have arranged our symplectic eigenvalues in a non-decreasing order. Now these blue vertical lines represent the symplectic eigenvalues that are equal to the mth symplectic eigenvalues, and these are the rest of the symplectic eigenvalues. Now this im corresponds to the indices that are less than or equal to m, corresponding to those symplectic eigenvalues that are equal to dm, and jm corresponds to the remaining symplectic remaining indices of this remaining indices corresponding to those symplectic eigenvalues that are equal to dm again. And rm is the sum of im and jm. With this, these remaining indices are m minus im in number, and these right side blue group has n minus m minus jm number of symplectic eigenvalues or number of indices. So with these numbers in mind, we also set up some other notations. Consider this set delta m of A. This is defined as the set of 2n cross 2m real matrices of the following form. So it consists of matrices of this block form. It has 4 blocks. Each block has same structure. Let me explain the first block. This I represents the m minus im cross m minus im identity matrix. And this U as well as V are real Rm cross Im matrices, such that U plus iota V are matrices with orthonormal columns, meaning it's a complex matrix. Its columns are unit vectors as well as orthogonal to each other. So this is the structure of this set. With these notations and structures in mind, we now give the expression for the Fenchel subdifferential of this map sigma m. So the Fenchel subdifferential of sigma m at A turns out to be the closed convex hull. This represents the closed convex hull of matrices of this form, where H varies over delta m A. So this Fenchel subdifferential of sigma m is characterized by matrices in this set delta m A. The proof of this particular theorem uses a part of our previous work and basic linear algebra. And this result is going to be key in calculating the directional derivative of sigma m as well as the map m. Before going to the next result, let me introduce a notion called symplectic column partition. If S is any real matrix with 2m columns and alpha 1 to alpha k are positive integers whose sum is m, then consider the following partition of the indices 1 up to 2m. The first partition consists of the indices from 1 to alpha 1 and m plus 1 to m plus alpha 1. The second partition is kind of a continuation of the first one. It is the set of indices starting from alpha plus 1 to alpha 1 plus alpha 1 to alpha 1 plus alpha 2 and m plus alpha 1 plus 1 to m plus alpha 1 plus alpha 2, and it goes on Again, to understand this partition, let me explain it with the help of a diagram. Suppose these vertical lines represent the two M indices, with blue representing the first M indices and green representing the next M indices. Then the first partition consists of the first alpha 1 indices from the blue part and first alpha 1 indices from the green part. The next partition consists of the next alpha 2 indices from the blue part and next alpha 2 indices from the green part, and it goes on and so on. So the last partition will consist of the last alpha k indices from the blue part and the last alpha k indices from the green part. So that is the structure of this partition. Now with this partition in mind, let us denote by S subscript ij the submatrix of S whose columns are indexed by ij, meaning it is a submatrix of S consisting of those columns of S that are indexed by this set ij. With these notations in mind, we call this partition the symplectic column partition of S of order alpha 1 up to alpha k. Now we state the theorem which gives the expression for the directional derivative of sigma m. In that theorem, A will represent an element of the set P2n, meaning it's a 2n cross 2n positive definite matrix. M will be a symplectic matrix obtained in the Williamson's theorem that diagonalizes A, meaning M transpose AM is equal to that diagonal matrix D00D. By I, we will denote the 2n cross 2n identity matrix. And this expression will represent the symplectic column partition of this identity matrix of order M minus IM, RM, and N minus M minus JM. Let us recall what these three numbers are again. M minus IM represents these indices, these blue ones. RM represents these indices corresponding to the symplectic eigenvalues that are equal to DM, and N minus M minus JM corresponds to these indices. So these are these three numbers. Again, define M bar and M tilde this way. For example, M bar is M multiplied from right with the matrix I bar and so on. Now for every 2n cross 2n symmetric matrix B, define matrix B bar this way and B tilde this way. Here B tilde is a 2Rm cross 2Rm symmetric matrix. We write this symmetric matrix in a block matrix form where each block has size Rm cross Rm. Then we have this expression. We have the expression for the directional derivative of these maps sigma m at A in the direction B, which is given by this expression trace of B bar plus the sum of first J largest eigenvalue of this matrix B double tilde, and these are IM in number. This matrix B double tilde is a matrix, is also it's a Hermitian matrix of size Rm cross Rm, which is defined as like this. It is the sum of these two matrices plus iota times the difference of these two matrices. If you sum this matrix and add iota times the difference of these two matrices, you get a Hermitian matrix of order Rm cross Rm, and this B double tilde is that matrix. So we have this expression for the directional derivative of this map sigma m. Let me quickly walk you through the outline of the proof of this theorem. I find this theorem very interesting, and its proof is also very nice. So what do we need to find? We need to find the directional derivative of this map. And we already know that sigma m are convex maps. So our max formula comes into picture to give us the directional derivative of sigma m. So it is given by this max formula. So it is defined as the maximum of inner product of C with B. So this is the expression for the directional derivative of sigma m at A in the direction B. It is the maximum of these quantities where C varies over the Fenchel subdifferential of sigma m. So this is the expression for the Fenchel subdifferential m. What is that expression? We recall that. This is the expression for the Fenchel subdifferential of sigma m. Now see that this inner product of C with B is a linear map in C. So this particular quantity is maximum of this linear map over a convex set, closed convex set. It is a property of linear maps that if you want to take its maximum over a closed convex set, it suffices to take its maximum over a subset of that convex set that generates that convex set. So the maximum in both the cases will be equal. So instead of having C vary over all the elements of this Fenchel subdifferential of sigma m, we can replace C with this specific matrices and get the same thing. So this expression is given by this quantity. Now here we only need to see what these expressions look like. So let us see what these expressions look like. Recall that H is of this form. So because H is an element of delta M and delta M has matrices of this form, here U, V are Rm cross Im matrices such that U plus iota V have orthonormal columns. Yeah. So a direct calculation leads us to this particular expression. So this expression is equal to trace of B bar plus trace of this Hermitian matrix. Now what we do is we take maximum over H, where H varies in delta M. So left hand side is nothing but the directional derivative of this sigma M at A in the direction B. Now taking the maximum right hand side. So taking maximum over H is same as taking maximum over U V, where U plus iota V vary over all matrices with orthonormal columns and of size Rm cross Im. So we get this expression. Now, this particular expression in the right hand side is a known quantity by a well-known result by Kifan, known as Kifan's maximum principle. It turns out that this quantity is equal to the sum of first Im largest eigenvalues of this Hermitian matrix B double tilde. With this thing in mind, if you replace this particular quantity with this in the right hand side of the above expression here, we get the expression for the directional derivative of this map. And this completes the outline of the proof. Now that we have the directional derivative expression for the sigma m, we will calculate the directional derivative of the maps dm in the following way. For m greater than 1, we can write the mth symplectic eigenvalue of A as a difference of these two quantities. You see, this is like negative the sum of first m minus 1 symplectic eigenvalues. This is negative times the sum of m symplectic eigenvalues. This quantity is nothing but half of sigma m minus 1 of A, and this is half of sigma m A. So therefore, we can define this dm A in terms of these sigma functions this way. Now, we know that sigma functions, these sigma m minus 1, sigma m, sigma 1, these are all convex functions and hence directionally differentiable. So by definition, dm is also a directionally differentiable function. And moreover, one can find the expression for the directional derivative of A directly. So this is the relation followed. So you take the directional derivative of dm, it turns out to be the obvious expression in terms of the directional derivative of the sigma functions. With these relations in mind, we get, using these relations, an expression for the directional derivative of this sigma j maps. We get the expression for the directional derivative of the dm maps, which turns out to be minus half times the imth largest eigenvalue of this Hermitian matrix B double tilde for all symmetric matrices B. The proof is pretty straightforward. It uses basic linear algebra arguments to come up with the expression. So we got the following things. We calculated the Fenchel subdifferentials of sigma m maps. We got the first order directional derivatives of sigma m. Using the first order directional derivatives of sigma m, we got the first order directional derivatives of these dm's. And this was what I wanted to talk about today. But actually there is more. We were also able to study, we also studied two other subdifferential properties of symplectic eigenvalues, namely Clark subdifferentials and Michael-Pinot subdifferentials. And we got some interesting results for these subdifferentials as well. One can also look at some natural directions and can explore. For example, there are other notions of subdifferentials. For example, Fresher subdifferential, epsilon Fresher subdifferential, several other subdifferentials are there. One can try to study the properties for symplectic eigenvalue maps for those subdifferentials as well. And one can also look at the higher order directional derivatives of these symplectic eigenvalue maps. Here are some important references that we used in our work. These are some books and reference papers. Thank you for your attention. Yeah, I'm done.
Yeah, any questions?
So Hemant, I have a question.
Yes, sir.
Yeah.
What do you do with these? You have got the subdifferential formulas. Any nice corollary application, variation, perturbation, something? Where are you using this?
For the Fenchel subdifferential case, that is that. Using the Fenchel subdifferential, the application of that, I would say we got the directional derivatives. And actually there are, I don't have any concrete application on mind in other fields as per se. But for example, using the subdifferential, using the expression for the other subdifferentials, such as Clark and Michael-Pinot subdifferentials, as a small application, we were able to get different proof for the monotonicity principle for the symplectic eigenvalues, which says that if A is less than or equal to B, then Jth symplectic eigenvalue is less than or equal to the Jth symplectic eigenvalue of B. So such kind of small applications we got. But actually the motivation was the importance of the symplectic eigenvalues in various other fields. So that was the motivation.
Yeah, it's very good. I mean, you've got interesting expressions. So in the book by Lewis, you will see for the classical Hermitian eigenvalue problem, some applications of these convexity theorems to the eigenvalues of Hermitian matrices. So you should look for similar things here.
So the same book that I mentioned, Convex Analysis by Lewis and Borwin and Lewis, is that you're talking about?
Yeah. And there are several papers on this, especially Lewis. he got proofs of some classical theorems on variation of eigenvalues, Leadsky and others using this subdifferential, I guess. So maybe you should look for those. And
Okay, sir.
it's good to have the formula, but it should also be used for something more.
Yeah, sure, sir. Yeah, that.
Thank you, sir. So any other question? Or comment?
Good talk. Good talk.
So how many people are there? How many people are attending?
It's quite big by our standards. It's 31 right now. The maximum was 34.
Good.
No, you see, it's easier because if you had a physical talk, I will not have been able to come.
Yeah.
I mean,
Exactly. This is the advantage now.
For getting COVID because of my back issue right now, I wouldn't have come to the physical talk, but this I can attend. So, good.
So if there are none, so thank you all for joining us, and thanks Hemant for a nice talk. And then let us close the session for today.